Hello, my name is Derek Robinson, and today I'm presenting on our paper titled Error Identification Strategies for Python Jupyter Notebooks. Jupyter Notebooks are one of many types of computational notebooks. Others include R Markdown, Azure, and Google Colab. All computational notebooks are immensely popular tools for data science tasks. However, Jupyter has been described as the de facto standard, and over 6 million are publicly available on GitHub. Some users of Jupyter Notebooks praise their ability to help them find errors, while others maintain the stance that debugging in Jupyter Notebooks is not a good experience. While we may know how users feel about debugging Jupyter Notebooks, we do not know how they perform debugging in Jupyter Notebooks. This leads me to our research question. What strategies do data scientists use to find statistical, data, and programming errors in Python Jupyter Notebooks? Our study used Jupyter Notebooks that were translated from R Markdown notebooks provided to us by McNamara et al. The R Markdown notebooks came pre-populated with data, statistical, and programming errors, and each of them covered two different topics: the 2011 Spain election and the NBA Player of the Week. Each topic had three different versions, A, B, and C. Versions A and B contained errors, while version C did not. Our data collection and analysis procedures use a conceptual replication of McNamara et al. Each of our 14 participants analyzed either version A or B of a given Jupyter notebook while thinking aloud. After the analysis was finished, a semi-structured interview was conducted in order to gain deeper insight into their process. The entire meeting was screen and audio recorded, resulting in 14 videos. The recorded meetings were then analyzed using open coding in order to arrive at our findings, which consisted of actions and strategies taken during error identification. We identified 12 atomic actions that were performed during error identification. Actions which participants always used include reading code in Markdown, writing and editing code, and using the search engine. Several other common actions were the use of documentation and other online resources, inspecting code output, as well as inspecting data frames and graphs. And finally, there were a few actions that were seldomly used, such as inspecting CSV files, reading error messages, and adding comments. When it comes to the use of online resources, documentation websites such as Pandas, Plot9, and Stats Models were the most common. Other common online resources include Q&A websites such as Stack Overflow, and tutorial websites such as Geeks for Geeks. Many of the previously mentioned actions were performed together to serve a particular purpose. We call a collection of these related actions a strategy. And overall, we identified 7 different strategies. Out of these 7 strategies which we identified, 2 were used by all participants: the search engine-driven approach and the assume and sometimes check strategy. The search engine-driven approach involves the use of the search engine and external resources to gather useful information. The assume and sometimes check strategy involves making an assumption related to the notebook and then sometimes checking it. The next most common strategy is the expectation confirmation strategy, in which the participant expects a code cell to do one thing based on its explanatory markdown. However, the code cell's behavior cannot be confirmed upon seeing its output. It should be noted that other researchers have found that in practice, explanatory markdown is seldomly used, and that may affect the efficacy of this strategy. The overall implications are that the identified strategies point to a need for more debugging tool support in Jupyter Notebooks. We also found that the re-implement to check and start with what you know strategies may be unique to notebooks, as other debugging literature has not pointed out anything that is similar. And finally, debugging notebooks differs in the following ways. The type of development is different in that when using Jupyter Notebooks, you are often doing data science related tasks such as information visualization and data wrangling. The development tools themselves are at different levels of maturity when it comes to debugging support. When developing traditional software within an IDE, you have a full suite of debugging tools to help you. This is not the case in Jupyter Notebooks. And while some strategies may be similar, they are often conducted differently in practice due to how notebooks isolate code cells from one another. Based on our findings that the re-implement to check and start with what you know strategies may be unique, we suggest the following tool support based on these strategies. The first is a tool which supplies the user with code snippets that use a different implementation so that they can compare the results of two different implementations to see if they are the same. This would facilitate the re-implement to check strategy. Next, we suggest a tool which provides code complexity measures for code cells so that users can compare their previous experience with the complexity of a code cell to gauge where best to start in the notebook. This would facilitate the start with what you know strategy. I'd like to thank all of my co-authors and collaborators for helping with this research and their contributions to it. Namely, I would like to acknowledge Kelly Bodwin and Ian Flores-Saika for sharing the initial R Markdown notebooks, Hunter Glanz for reviewing our Python notebook translations, Amelia McNamara, Amal Abdel Ghani, Philip Burkhardt, Allison Theobald, and Greg Wilson for the study idea. And finally, I would like to thank all of you for listening. Thank you.